All right, and we are live. So, welcome back for another chapter, diving into the GPUs until fused kernels. And we're still reading the ultra scale playbook, and hopefully we're kind of wrapping up already. So I think it's well, the next meeting is going to be the last one. Um, but anyhow, today it's about GPUs until fused kernels. Um, and what we need to know about GPUs is essentially like the high level blueprint of how they function. So each GPU um, has dedicated, well, streaming modules, SMs. So they have multiple cores inside of these SMs. And these SMs, they have their own individual pieces of memory, kind of cache, and then the overall GPU has like this global memory. That's what we usually refer to when we see the amount of memory on a for instance one H100. So when we say that it has 8 gigs of memory, it's usually referred to the global memory, but then the actual execution happens on these SM modules. Each one of them has their own dedicated small piece of memory, and inside of this SM module, they have the actual cores, multiple cores that do the actual execution. Um, and in terms of, well, and this execution happens in parallel. And in terms of actual numbers, we can see that, for instance, H100 has this 132 these SM modules. And then inside of this, inside of each of these SM module, they have 128 cores, which amounts to 16,000 cores on each one of the GPUs. And we can see that, well, basically the speed up that we see with each generation can be attributed to, well, I think either increased number of cores or, yeah, like for instance, when we jump from A100 to H100, we see a drastic change in the number of cores. And also the memory bandwidth also increased. So we have higher memory bandwidth and we have more cores, which results in faster computation overall. And once again, a bit more detailed view into how these SM modules are organized. So we have this global memory, which is like our largest memory. We have a shared cache, L2 cache across, which is faster memory, that is shared across multiple SM units. And then each one of these SM units has their own cache, shared memory thing. And each one of the SM units schedules, kind of independently schedules the execution onto their own cores. And when we write our code for the GPUs, we usually do it in either CUDA or Triton, and then this CUDA Triton code is compiled to the so-called parallel thread execution assembly, which is like assembly for NVIDIA. And we're currently talking about only NVIDIA GPUs. So the book doesn't mention how like this picture would look like on other hardware, but I believe that it should be something pretty similar. So each one of the hardware kind of types should probably have their own assembly language that does kind of schedules the actual instructions on the kernel, and we probably are going to be using some sort of high-level language, like well, CUDA for NVIDIA, some other level of abstraction for other hardware modules that is going to be compiled to this assembly language. And to get an idea, in the book they give us the code that is that runs on our CPU, our host code, and we have the device code that is actually being run on the device. So apart from like the instructions that are being run on the device, we also should have instructions that should run on our host, on the machine, on the CPU. So kind of the kind of centralized piece that orchestrates the data flow between multiple GPU cores and aggregates this data and does something actually useful with this data once we do the computation. So here we can see that we kind of allocate multiple pieces of memory. Well, I think we copy, yeah, we copy vectors from host memory to device memory, and then the actual device code that schedules the computation on the device is this vector add. It's right here. Um, so that's what actually is being executed on the device. Basically, we just add some numbers and then we copy the results back. All right. So back to the SMs, streaming multiprocessors. We need to understand one more thing about them. That so far we covered that there are multiple SMs on each one of the GPUs, and each one of the SMs has multiple cores, and they execute the same instruction on these multiple cores in parallel. But it's not the whole picture. What actually happens is that these SMs also group the threads that are executed on the multiple cores in parallel in so-called warps. So I don't have a very good idea why they do that, probably because it's easier from the scheduling perspective and the book doesn't cover it, and I didn't have a chance to dive deep into that yet, maybe later on. But that's how it functions, at least from what we've been told in the book, that each one of these SMs, they don't actually schedule each one of these threads one by one. They organize these threads in warps, and they actually schedule parallel execution on multiple cores at once when they organize these threads slash cores into a single warp. Probably because it's very, very high speed computation. I think it's just easier that way to probably parallelize the execution when since each one of the cores executes inside of a warp executes the same instruction, it's probably just easier to fetch these instructions and kind of broadcast the same instruction to multiple cores at once. But I mean, like, I don't have an explanation just yet about why it's 32 and why we can't like schedule. Why do we even need warps? Why can't we just go from one SM to threads? I mean, like, it's probably going to give us less granularity, right? But still, it's kind of a mystery for me at this point. However, we have 6 people on the call. So, do you guys have an idea why we need warps when we go from SMs to threads?
Um, what I have read is that warps, all the threads in a warp are executed physically in parallel, and this allows you to avoid some synchronization between the threads.
Yeah,
So,
but
like,
like, yeah, but why? I mean, like, well, say we have. Let's go back to the numbers, right? That we had.
yeah,
So on a H100 we have 132 SMs, right? And if a warp is 32 cores, threads, I think they're interchangeable, right? So threads, cores, whatever. So it means that each one of the SMs operates can operate on 4 warps at the same time, right?
yeah.
At least,
Uh,
yeah.
Again, like this is all about parallel, like physical guarantees of parallelism. And this is exactly to avoid some synchronizations.
Yeah, sure, but why do we even need warps? say, why don't we increase the number of SMs by 4 and we just remove the warp abstraction entirely? Why can't we go with, I don't know what, 500 and something SMs that like, and make each SM operate a single warp? So kind of, like remove
I
this
don't know
hierarchy.
beyond that. This is a nice number that is translated across all architectures. So it's basically like just some design choice that was made long ago, and that is like applicable across all the GPUs.
Yeah, yeah. Well, does anyone else have any ideas? My guess
It's
it's probably related to some kind of physical constraints, so probably you just can't physically, for some reason, kind of have more SMs, right? So we can see that actually the number of SMs from A100 to B200, well, it increased by 2 times, which is kind of a lot. But at the same time, well, we also scaled the number of cores only by 2 times. I don't know.
it seems the 32 thread warp size is kind of historical artifact since 2006, and you have like basically 4 separate blocks. This 128 is like 4 separate blocks of 32, and you don't really want 2 large warps because, as you know, like there is divergence.
Yeah, sure, I get that. So like
And,
the smaller the warp is, the harder it is to kind of schedule stuff on this warp, right? The harder it is to kind of well, the more synchronization issues you're going to have. So it makes sense. What doesn't like well, not necessarily doesn't make sense for me. What makes me question things is that why, like, if we stuck with this 32 size for historical reasons, why do we need SM to operate on 4 warps? Why don't we just merge one SM and one warp into a single unit of abstraction, if it makes sense?
mm,
So, like right here, for instance, why don't we say that each SM has only 32 cores, effectively one
mm.
warp, and increase the number of SMs by 4 times?
Well, SM is also associated with some cache memory, and then yeah, it could be just like
Oh, okay. So you're saying that basically the idea is that it's a way of kind of having hierarchical cache, right? So we have multiple parallel units of execution that they that are going to share the same cache. But then we
Mm,
also have another layer of parallelism when we have multiple SMs that share the same cache, right?
mm.
Okay, yeah, kind of makes sense. I can buy it. All right, all
I
right.
assume it's like just a trade-off choice. It could have been either way. But,
Yeah, we'll probably well, you probably need to be much more involved into writing these CUDA kernels from scratch on daily basis for multiple years to have a very good understanding of why we need this kind of granularity exactly. But anyhow, it's just something I thought of and I didn't have a very good answer. Now we have, I guess, a semi-good answer. All right, I'm ready to move on if you're ready. All right, let's move on. So we were here. Yeah, here actually. And we can also see this blocks thing. So, to my best understanding, when we actually schedule something on the kernel, on the GPU kernel, we actually schedule it in blocks, and then these blocks they kind of been distributed to different SMs. So it's multiple layers of grouping operations together. All right. In the book we have a simple example of what we can start with on how we can translate our Torch Python code into the effective kernel. So we have this elu operation, which is well, it doesn't. I think it doesn't really matter what it is. What really matters here is that we have some sort of branching and different paths of execution. But basically, we have the identity and exponentiation. And in Torch, we would write it like we would write it with something like this. Then when it's below 0, we do exponentiation, otherwise we just return identity, and we have this torch where, so basically the branching. And the first thing that we can do, we can throw torch compile on top of it. And torch compile, it's going to use the built-in compiling torch to try to kind of avoid going from GPU to CPU to do this where operation. At least that's my understanding, and do everything on the GPUs. And we'll later see what the code actually looks like, the assembly code. And they give us the numbers, and the numbers are stunning. So without torch compile, with just regular torch, which doesn't have this efficient kernel rendered. Well, I think that the performance is like what, it's 6 times slower than with torch compile. And well, why we don't have a list of instructions presented without torch compile. We can see what happens when we do torch compile, and when we pass this output code thing. So this is what is actually being compiled by torch to a Triton kernel. And this is the annotated version that is much easier to read for us. Well, what's the next slide, by the way? Yeah, I think I duplicated slides. Lovely. Let me just remove this one quickly. All right, so we have basically what happens here is that well, it's a Triton code, and Triton, as we can remember, is another layer of abstraction, kind of lower level than Torch, that we go from Torch to Triton, then the compiler compiles it to the assembly. And I think I was lying, so I don't have an assembly thing here. All right, well, poor me. Anyhow, this is the annotated Triton kernel that's going to be further down the line compiled to this PTX thing. I guess without the actual PTX thing, without diving deep into the how Triton works, I don't think it makes too much sense to dive deep into what's written here. But I see we have George on the call, and George is a master of Triton, at least to my understanding. So maybe George would have any comments, kind of anything to add here. George, would you?
Hey guys, yeah, I couldn't be unnoticed here. Hello everyone. So Triton is a high-level language that can compile to PTX, and every operation has its already like auto-generated code from the PTX side. This is different from CUDA, where you actually have a bit more control. But if we actually discuss that kernel a bit, then we could see that there is so Triton, I don't know if Andrei already discussed this, but it's a tile level language, which means that we operate on tiles, which is a block of memory, and most of the operations in GPU basically operate on a tile as a whole. So they can, for example, run vector addition for the whole tile, and for that reason, it's really important to optimize for like a singular operation for that tiles. For example, in the line, which is like the second line of the kernel, block indices, right? We initialize the address in the memory where we start our tile, and the arrange, which we basically specified the tile size, which is block size here, as an argument. And we read those indices at the same time with the tl.load. By addressing the input pointer, which will be kind of easily converted from torch. So torch gives you the address of the tensor in the memory whenever you create it or even not create it. So if you initialize it as torch.empty or some other like torch.once, but on CPU, for example, you can give the pointer to the Triton compiler to access that. So it's basically zero memory copy. So you have this pointer, you specify the indices to load. Usually this is contiguous in memory. So it means that you, in order for load to run efficiently, you want those indices to like be contiguous in actual GPU memory, which is not the case for most of the recent architectures such as Blackwell. So for that reason, you have to like do some Swizzling magic in order to make those indices work properly. And the third argument, or like second valid mask, is basically how to read this without basically going out of bounds. So mask is helpful here to specify the exact number of elements to load, which has to be a power of 2. So that's how memory in a GPU works. And if you need less, you specify those masks. And yeah, actual values are usually easy. For this particular kernel is running exp, which is also like optimized operation on GPU. So it has its own auto-generated code running on the background, and yeah, in the end we store some values after we compute those values into the new memory in the output pointer. So it's pretty easy for the like kernels like ILU, for example, when you just do this like pointwise operation on every element that you read, and you just write it to different area in the memory. I think it gets much more complicated when you have to arrange those memory in between each other if you do some extra work with flash tension kernel, which is a good and proper example to study. But overall, I think Triton is really good to use for pointwise kernels because it basically provides you easy access. So for any pointwise kernels, just read a huge chunk of memory, run the same operation, which is optimized on GPU, and then store. So yeah, that's my comment for now.
Awesome. Yeah. Thank you very much. Yeah, and basically, as you mentioned, that the limitations of Triton is that I think like the book mentions that like you can't do like granular intra SM scheduling. So intra SM, I believe it's kind of like inside of a singular SM unit, right? So and also you have limitations in terms of how you can operate shared memory inside of SM. So the Triton assumes this that you operate on these tiles, and if you need to kind of have more lower level control of the shared memory management or intra-SM scheduling, then you have to go to CUDA level. All right. I think that what we really need to kind of remember from here is that when Torch compile, the output of Torch compile, when we provide this Torch logs output code, can be probably a good starting point to start optimizing the kernel manually if we want to. Or like not manually, like I heard that Opus 4.5 is quite good at optimizing kernels these days. So, well, and how can we optimize stuff? So one of the techniques that we've been presented with is memory coalescing, and here's the basic idea is that when we read data from shared DRAM, and shared DRAM, I believe it's been referred to this stuff, so global memory. So when we read stuff from there, we actually never read a single bit. We read blocks of the data, kind of, and whenever we need to access a single address, we actually the amount of memory that's being transmitted to memory controller, it's actually a block of memory simultaneously. So if we're not very smart about how we access this memory and we have multiple random accesses in different parts of memory, we would be very inefficient in terms of utilizing the throughput of the bus between the shared memory, the big shared memory, and the memory on the each one of the SMs. and we would kind of each one of these random accesses would have their own burst. Well, they call it burst, but like basically a huge chunk of memory that's being read, that's being transferred, and then we read only part of this chunk and discard the rest, so very inefficient. And when we coalesce the memory access, when we make it sequential, that means that, well, say on the SM, inside of the SM module, we want to get sequential data from the shared GPU memory, and that means that it's going to be a single transfer from the shared GPU memory to the memory controller. So lovely, very efficient. At least it seems efficient. And we can see how it can be applied to matrix multiplication. So we're being given a naive algorithm to do matmul, and what we need to get from here is that for naive matmul, we think that, well, we think in blocks, and we think each block is kind of mapped to each one of the SM units, for instance. And then inside of this, each one of the SM units, we have multiple threads, right? So, and in the naive matmul, we'll assume that each one of the threads is going to calculate only one element of the output matrix as a whole. And to calculate one element of the output matrix, well, for instance, this guy with position X and Y, we need to get the entire row X, right? We need to get the entire column Y, and we need to do the dot product between them. And that's exactly what this algorithm does. So we calculate the, well, we get this position X and Y somehow. And then what we do is we access in this loop, we access the entire row and we multiply it element-wise by the entire column. So this is our dot product. And we need to know one thing to argue about the efficiency, is that matrices in the GPUs are stored, at least like that's what the book provides us with. In the row first, or like row-wise fashion, meaning that each one of the rows is sequential, and then, which basically means that if we traverse the row, we get sequential data access. But if we traverse columns, we will need to jump, right? And that means if we go back to this bursting, if we traverse columns, for instance, from A00 to A10, A20, we would have 3 bursts. Burst for like these elements, burst for these elements, and burst for these elements. Unlike with the rows, if we try to access 3 elements in a single row, it's going to be a single burst of memory. Which brings us to this memory access pattern from the blog post linked to that book, that in that naive algorithm, each one of the threads is going to access different rows, and each one of the rows is going to have continuous memory access, but we will be traversing different rows, right? Because it's different threads. But then when we try to get a single column, this column is going to, well, it's not continuous, and so it's going to be multiple bursts of memory, and the threads are going to be competing for the same memory access of the column. Bad things. And the proposed optimization is that instead of traversing, so the result before was that if we access a single column and different rows, like with this algorithm, I believe that's what we're doing actually. Then what we get here is we get the column, like the resultant column. If we modify our algorithm to map, to force our threads to calculate the same, like iterate through the same row, but go through different columns, then we will first wind up with the resulting cells in a row. But what's more important here is that we remember this, that accessing a row, it's continuous memory. Accessing a column one by one, it's not continuous. However, if we, since multiple threads operate in parallel, if all of these threads span across multiple rows, then it means that in the first iteration, when we try to access, say we have 3 threads, right? If 3 threads try to read the first element of each column, since these elements are adjacent in a single row, what is going to happen that only a single row is going to be read from the GPU memory and transferred in a single burst, like this one row. And then all of these threads in parallel, they are going to go through this row and they're going to multiply it by the first elements of the column, then by the second elements of the column, third elements of the column, fourth elements of the column. So what we'll get this coalesced, merged, or single burst of memory reads when we operate on multiple columns at the same time if we make threads traverse them in parallel. And threads are made to traverse. And that's exactly how the scheduling is done. So GPU schedules the same instruction to execute on multiple threads in parallel. And since this same instruction, well, it's basically going to be the same loop. But since we've been smart about how we make the indices, that means that we're going to have a single burst of reads spanned across multiple columns. Hopefully, I hope it makes sense. And the results, the results are stunning. So the naive, at least from the blog post, I didn't measure it myself. So the naive implementation memory throughput was 15 gigabytes of data per second. Then we reach 110 gigabytes, so roughly 7x improvement. And also with coalescing, the overall number of floating point operations, it grows from 300 gigaflops to 2000 gigaflops. It's still far from ideal because the advertised compute throughput of this of that GPU, I think it was H100, but nevertheless, the advertised optimal throughput was 30 teraflops, so we're still very far from that, but it's still much better. It's already much better, right? Anyhow, so we have memory coalescing. Another optimization is tiling. So that's what George told us about. That's about these mysterious tiles that Triton operates on, right? And I believe this concept of memory optimization called tiling is kind of similar, adjacent, if not the same, that we have in Triton. So the idea is that, when we want to do a matrix multiplication of A by B and resulting C, we once again need to go through each row, through each column, right? So to get this element, we need to go through this row and do the product of this column. And we can notice that we can actually go through this part of the row and through this part of the column, and then add another dot product of the rest of the row and the rest of the column. And it makes sense because of the I believe it makes sense because of, once again, these memory bursts, and because of how once again, I believe in my view, it makes sense because of how data is being transferred from the shared memory to the memory in the memory controller. So once we transfer a single tile, then we can reduce the number of the data transfers from the shared memory into the controller memory when we force, with our code, in our code, we force all of the threads to first reuse and do all of the computation of the data that's already in memory in the shared, in the shared memory, and in the control memory, sorry. And then after we've done all of the computation inside of across all of the threads for this piece of data that we transferred, that probably fits optimally into the throughput of what we can possibly transfer from the shared memory to the controller memory. Then we read the next couple of chunks and we do the same thing. And in terms of code, what really changed there, if we compare it with this code, is that now, well, we have this tile size. Yeah, and I think I have a better version of this code right here. So it's a bit easier to read. So basically, instead of going through entire row, we now go tile by tile, and we aggregate this. And we aggregate the final result across multiple tiles right here. And at last, well, not at last, we still have one other thing, but at last-ish, we can also try to be a bit smart about what kind of operations we're doing inside of on a single tile in a single thread. So if we examine how much time we spend in the and on what we spend this time inside of the kernel when we're doing our computations, we can notice that with the current kernel implementation, a lot of time is being spent on this something called MIO throttle. And I believe this MIO throttle is this stuff, so think threads. Oh no, I don't think it's sync threads. I think it's data read from, well, actually, yeah, I think it's think threads, so like kind of sync threads. So we ensure all threads in the block have completed data loading. So it's kind of here, but it means that, yeah, it's actually spent on the data loading that precedes this thread synchronization to do the data reads. And what we can do is actually, and this is not from the book, this is from the blog post associated with this chapter of the book, that we can notice that a single thread can probably compute multiple values at once. So if since we already have this kind of tile transferred for each one of the matrices, we can try to force each one of the threads to do the computation across a piece of the row for multiple elements at once. And that means that we won't be waiting that much for each one of the elements, because we read once, then we do multiple operations at once, and then we do another memory read. At least that's what we've been told. And the results from the blog post, well, I wouldn't say that it's a drastic improvement, but still, in the background we see the old results. So we can see the decrease in this MIO throttle thing. And the last optimization that we been proposed in the book is to minimize control divergence. And the idea is that each one of the warps inside of a SAM is going to execute the same instruction. So if we have branching inside of our host code, so for instance, if part of the warp has to do one part of the branch, and the part of the warp has to do the other part of the branch, the scheduler can't really schedule different instructions inside of the same warp. It has to do them sequentially, and that means that the part of the warp is going to be waiting for the second part of the warp is going to be waiting for the first part of the warp to complete its branch execution, and only then it's going to be able to execute the second part of the branching, if we have this branching. So the idea is that try to avoid branching at all costs, and if you have to do branching, try to be smart about it and think how you can force a single part of the branch to be executed on the entire warp at once. So that's basically it. I guess I have more questions than I have answers at this point, and probably the best way to do it is to start writing Triton kernels manually and finally implement this flash attention by hand. Still haven't done that, well, hopefully I'll have time to do it in February. Do you guys have any questions, comments, or anything else to discuss?
Thank you for your explanation.
Thank you for being here, and thank you for your comments about Triton. Alright, so since we don't have any further questions, then see you in a week for the second part of this presentation. And it's not going to be me, it's going to be Igor, who is going to probably do a much better job, as always, presenting us with the fused kernels. Yeah, see you in a week and have a good week. And I stopped sharing and I have to stop recording.